Good day, everyone. Welcome back to Almighty Choice Tutorials. In today's lesson, we are covering Chapter 1.9, Intermolecular Bonding. This topic explains the forces that hold molecules near each other, and it directly links to the boiling point, melting point, states of matter, and solubility. Keep your notes ready because this chapter appears in many exam explanations. All right. Here is our complete lesson roadmap. We will begin by separating intramolecular bonds from intermolecular forces because that's the most common confusion. Then we'll work through the dispersion forces, dipole-dipole forces, and hydrogen bonding. After that, we will connect these forces to boiling points, melting points, water, ester applications, and exam questions lesson, you should be able to define intramolecular and intermolecular bonding accurately. You should also be able to describe dispersion, dipole-dipole, and hydrogen bonding, and then use the structure, polarity, and size to compare substances. Success today means you identify the force, compare its strength, and explain the effects and justify your answers using correct chemistry language. Focuses on the difference between the intramolecular and intermolecular bonding. All right, everyone, this is probably the most foundation slide in the whole topic because students constantly mix up intramolecular and intermolecular bonding. So let's break it down clearly. Let's start with intramolecular bonds. The word intra means within. So the intramolecular bonds are within the molecules or compound. In the water, the solid lines show the covalent bonds between oxygen and hydrogen. These bonds are strong and they're not the same as the weaker forces between separate water molecules. Intermolecular forces. The word inter means between. So intermolecular forces act between the molecules. As you can see on the screen, these are two different water molecules, one, and this is the other one. The dotted lines represent the attraction between the two water molecules. These forces are weaker than covalent bonds, but they control the physical properties such as boiling points, melting points, and whether the substance is solid, liquid, or gas. It's very important that these keywords are used accurately in your exams. Intramolecular means the bonds within a molecule, while intermolecular means the forces between the molecule. A dipole is a separation of partial charge, meaning one end is slightly positive and the other is slightly negative. A polar molecule has a positive and a negative end, while a non-polar molecule has no overall permanent dipole. So this comparison table is also very important. Intramolecular bonds are within a molecule and they are usually very strong. Intermolecular forces are between the molecule and they are much weaker. During the phase changes such as melting or boiling points, the intermolecular bonds do not break. Instead, intermolecular forces are weakened or overcome. So now, this is a critical exam warning. When water boils, the OH covalent bonds do not break. The water molecules remain H2O molecule. What changes? Just the hydrogen bonding between the water molecules. So never write covalent bonds break when water boils. The correct wording is the intermolecular forces are overcome or weakened. All right. So this slide quickly summarizes the difference between the intramolecular and the intermolecular bonding. On the left, intermolecular bonds are strong bonds within a molecule like OH covalent bonds in water. On the right, intermolecular forces are the weaker attraction between molecules, such as hydrogen bonding between neighboring water molecules. The key exam idea is here at the bottom. During phase changes like boiling or melting, intramolecular bonds stay intact and the only intermolecular forces are weakened or overcome. So remember, within the molecule, strong chemical bonds between the molecule, weak intermolecular attraction. Now, part 2 introduces the three main intermolecular forces. We will move from weakest forces to the strongest force. As you learn each one, keep asking which molecule have it, how strong is it, and how does it affect the boiling point. So there are three main intermolecular forces. Dispersion forces are weakest and they occur in all molecules. Dipole-dipole forces occur in polar molecules and are usually medium strength. Hydrogen bonding is the strongest of all three and occurs when hydrogen is bonded to fluorine, oxygen, or nitrogen. Remember the order. Dispersion is less than dipole-dipole and which is less than hydrogen bonding. This flowchart helps you identify the strongest intermolecular forces. First ask, is hydrogen bonded to fluorine, oxygen, or nitrogen? If yes, hydrogen bonding is usually the strongest. If not, ask whether the molecule is polar. If it is polar, the strongest force is dipole-dipole. If it is non-polar, the main force is dispersion only. Dispersion forces are caused by temporary dipoles. Electrons move randomly around the atoms and molecules, and sometimes the electron distribution becomes uneven for a moment. This creates a temporary positive site and a temporary negative site. These are also called instantaneous dipole or the London dispersion forces, and they are present in all the molecules. This diagram shows temporary dipole formation. When electrons shift to one side of the molecule, that side becomes slightly negative and the other side becomes positive. This temporary dipole can induce a dipole in a nearby molecule. The attraction is weak because the charge separation is temporary, but it still matters, especially in large molecules. Here is the step-by-step process. First, the electrons shift temporarily to one side. Secondly, a temporary positive and negative ends are formed. Third, a nearby molecule is induced to form a dipole too. And then opposite partial charges attract. That weak attraction is a dispersion force. That's why even non-polar molecules still have intermolecular forces. Okay, so the first factor affecting dispersion strength is the number of electrons. More electron means a large electron cloud. A large electron cloud is easier to distort, so stronger temporary dipole forms. This is why iodine and the large hydrogen carbon have stronger dispersion forces than helium or hydrogen. In general, large molecules usually have higher boiling points. The second factor is molecular shape. Long or straight molecules can touch each other over a large surface area, so their electron clouds attract more strongly. Branched molecules often have less surface contact, so their dispersion forces can be weaker. Even if the molecule mass is similar, shape affects how closely molecules can pack together. Here we compare weak and strong dispersion examples. Small molecules such as helium, hydrogen, fluorine, and methane have weak dispersion forces and are often gases at the random temperature. Larger molecules such as octane, wax, and iodine have stronger dispersion forces, so they are more likely to be liquid or solids. Let's check the idea using carbon dioxide and nitrogen. Both carbon dioxide and nitrogen are non-polar, so both mainly have dispersion forces. Carbon dioxide has more electrons and a large electron crowd than nitrogen. Therefore, carbon dioxide's stronger dispersion forces. A stronger model answer should mention electron, electron cloud size, and the stronger dispersion. Part 3 is about dipole-dipole forces. These forces occur only in polar molecules. As we go through this section, forces on how permanent partial charges attract each other. Dipole-dipole forces are attraction between permanent positive and negative ends of the polar molecules. A polar molecule has an even distribution of charges. The charge is slightly positive at the end of molecule attracts the slightly negative end of another. For molecules of similar size, dipole-dipole forces are usually stronger than dispersion forces. This slide shows polar molecules with delta positive and delta negative end. The symbol delta means partial charge. The attraction happens between delta positive end of one molecule and the delta negative end of the another molecule. Because these dipoles are permanent, the attraction is stronger than a temporary dispersion attraction in a similar sized molecule. This table separates the polar and non-polar molecules. Polar molecules have an overall permanent dipole, so they have both dispersion forces and dipole-dipole forces. Non-polar molecules have no overall permanent dipole, so they have dispersion forces only. Remember, dispersion forces occur in every molecule, including polar molecules. Now, compare HCl and bromine. Hydrogen chloride is polar because hydrogen and chlorine create a permanent dipole. So HCl has dispersion plus dipole-dipole forces. Bromine is non-polar because it is made up of two identical bromine atoms. So it has dispersion only. For a basic comparison, HCl has stronger intermolecular bonding due to dipole-dipole attraction. Here is the extension point. Dipole forces are usually stronger than dispersion forces for smaller size molecule. However, very large molecules can have very strong dispersion forces because they have many electrons. For example, Hi has higher boiling point than HCl because Hi has more electron and stronger dispersion forces. So always consider both polarity and molecular size. Part 4 is hydrogen bonding. This is one of the most important sections in intermolecular bonding. Hydrogen bonding explains many unusual properties of water and often appears in boiling point and solubility questions. Hydrogen bonding is a very strong type of dipole-dipole attraction. It occurs only when hydrogen is bonded to fluorine, oxygen, or nitrogen. These atoms are highly electronegative. So, they make hydrogen very partially positive. Hydrogen bonding has a strong effect on boiling point, melting point, and solubility. Use Fon rule to identify hydrogen bonding. F stands for fluorine, O stands for oxygen, and N stands for nitrogen. Hydrogen must be bonded directly to fluorine, oxygen, or nitrogen. If hydrogen is bonded to carbon, phosphorus, sulfur, or chlorine, it does not count as hydrogen bonding under this rule. Hydrogen bonding is strong because fluorine, oxygen, and nitrogen pull electrons density away from hydrogen. This leaves hydrogen very exposed to strongly delta positive. Nearby molecules can approach closely and attract this exposed hydrogen. In the diagram, solid lines show covalent bonds and the dotted lines show the hydrogen bond between the molecules. There are two main requirements for the hydrogen bonding. Number one, hydrogen must be covalently bonded to fluorine, oxygen, or nitrogen. And secondly, a neighboring molecule must have a lone pair on fluorine, oxygen, or nitrogen. If one of these requirements is missing, you should not identify hydrogen bonding. Water is classic example. In each water molecule, hydrogen is bonded to oxygen, so water can form hydrogen bonds. The solid OH lines are covalent intramolecular bonds, and the dotted lines between the water molecules are hydrogen bonds. This network is why water has unusual properties. Ammonia can also form hydrogen bonds. In NH3, hydrogen is covalently bonded to nitrogen and nitrogen has a lone pair. This allows one ammonia molecule to attract another through an NH2NH interaction. An exam diagram show the hydrogen bond as a dotted line between hydrogen delta positive and the lone pair on the nitrogen. This table helps you to identify the strongest intermolecular forces. Methane is non-polar, so dispersion is strongest. HCl is polar but does not have H bonded to fluorine, oxygen, or nitrogen. So dipole-dipole is strongest. Ammonia, water, and CH3OH have an NH or OH bonds, so hydrogen bonding is strongest. Here we compare ethane, methanol, and methanol. Ethane has dispersion only, so it has a lowest boiling point. Methanol has dipole-dipole plus dispersion, so it's higher. Methanol has hydrogen bonding, dipole-dipole, and dispersion, so it has a highest boiling point. More energy is needed to separate methanol molecules. This slide reminds us not to ignore the molecular size. Larger molecules have more electrons, larger electron clouds, and stronger dispersion forces. This can make boiling points higher even when hydrogen bonding is not present. In exams, answers mention the force type, strength, size or mass, number of electrons, and the energy required. Hydrogen fluoride and hydrogen chloride is a key comparison. HCl has a more electron than HF and is polar, So it has dipole-dipole forces. However, HF has hydrogen bonded to fluorine, so HF forms hydrogen bond. Hydrogen bonding is much stronger, so HF has a higher boiling point than HCl. Part 5 connects intermolecular forces to states of matter, boiling points, and phase changes. This is where we apply the bonding knowledge to explain what we can observe in the lab. The physical states of substance depend strongly on intermolecular forces. Strong forces keep particles close together, so solids are more likely. Medium forces allow particles to move past each other, giving liquids. Weak forces allow particles to move far apart, giving gases. Temperature and pressure also affect the state. Look at the particle diagram. In a solid, particles are tightly packed in a fixed position and vibrate only. In a liquid, particles are still close together but can move past each other. In a gas, particles are far apart and move freely. These differences are linked to the strength of attraction between the particles. Boiling point is the temperature at what the liquid becomes a gas. At boiling point, intermolecular forces are overcome enough for the particles to separate into a gas state. Melting point is the temperature at which a solid becomes a liquid. During melting, intermolecular forces are weakened, but intramolecular bonds remain intact. This heating curve shows how energy changes temperature and state. On the sloped section, the substances warm up. On the flat section, energy is used to weaken or overcome intermolecular forces during melting or boiling. The flat section do not mean covalent bonds are broken. This is a golden rule. Stronger intermolecular forces mean higher boiling and melting point. Stronger forces require more energy to overcome. If more energy is required, the temperature must be higher before the substance changes state. This is a link you must write in exam answers. Part 6 applies intermolecular bonding to water, application and summary ideas. We will look at why water behaves unusually, how substances dissolve, and how distillation uses boiling point differences. Water has several unusual properties because of hydrogen bonding. It has a relatively higher boiling point and melting point for such a small molecule. It also expands when freezing and dissolves many polar and ionic substances. The reason behind this property is the strong hydrogen bonding network between the water molecules. Ice floats because of its open hexagonal structure. In ice, water molecules form hydrogen bond in a lattice that keeps molecules further apart than in a liquid water because the particles are more spread out. Ice is less dense than liquid water. That is why ice floats. Water is an excellent solvent because it is polar and can form strong attractions. The oxygen end is delta negative, so it attracts the positive ions. The hydrogen ends are delta positive, so they attract the negative ions. Water can also hydrogen bonds with many polar molecules, helping them dissolve. Alright, this slide shows simple distillation in a more visual way. The key idea is simple distillation separates liquid based on the boiling point. First, The mixture is heated in a round bottle flask. The liquid with the low boiling point vaporizes first and turns into gas. That vapor travels into the condenser. Cold water flows through the condenser, cooling the vapor back into the liquid. Then the pure liquid called the distillate drips into the receiving flask. In this example, water is collected as distillate while the salt stays behind. So remember the exam link. Weaker intermolecular forces mean lower boiling point, so that the substances distill first. Stronger intermolecular forces means higher boiling point, so more energy is needed. Esters are organic compounds found in fragrances, perfumes, and artificial flavoring. Isoamyl acetate, for example, has a banana smell. Esters contain a polar carbonyl bond, so they can have dipole-dipole forces. Many esters cannot make hydrogen bonds with themselves because they do not have OH or NH bonds. Isoamyl acetate cannot make hydrogen bond with itself, but it can interact with water. The oxygen in the ester group can accept hydrogen bonds from water. So with water, we can show a carbon and oxygen interacting with HOH through a hydrogen bond. This helps explain interaction between ester and polar solvent. Boiling point elevation links back to the attraction and energy. If adding another substance increases the overall attraction between the particles, more energy is needed to separate them. More energy means a higher boiling point. In exam answers, always connect the stronger forces to more energy required and then a higher boiling point. Okay, so this summary table brings the three forces together. Dispersion forces come from temporary dipoles and occur in all molecules. Dipole-dipole forces come from permanent dipoles in polar molecules. Hydrogen bonding is a special strong dipole-dipole force when hydrogen is bonded to fluorine, oxygen, or nitrogen. The strength order is dispersion, then dipole-dipole, and then hydrogen bonding. So here we have some key exam rules. Intramolecular means within a molecule and intermolecular means between the molecule. Stronger intermolecular forces usually give higher boiling and melting points. During phase changes, intermolecular forces are affected, not covalent bonds. Larger molecules have stronger dispersion forces and hydrogen bonding requires hydrogen bonded to fluorine, oxygen, and nitrogen. These are the common mistakes to avoid. Do not say covalent bonds break during boiling. Do not forget that dispersion forces occur in all molecules. Do not call every hydrogen containing molecule hydrogen bonding. Do not ignore molecular size and hydrogen number. And never say non-polar molecules have no intermolecular forces. They have dispersion forces. Alright everyone, before we finish up, here is your exit ticket. These questions are designed to check whether you truly understand the big ideas from this chapter. I want you to answer each question in about 3 to 5 sentences using proper chemistry terminology. Don't just give one word answers. Explain your reasoning clearly, just like you would be in a VCE exam. For example, if you're comparing boiling points, make sure you mention the type of intermolecular forces, the strength of the force, and the energy required to overcome it. Remember, stronger the intermolecular forces means higher boiling points because more energy is required to separate the molecules. Also, make sure you use Fawn rule correctly when discussing hydrogen bonding. Take your time, Think carefully and try to write scientifically accurate explanations. These are exactly the kinds of questions that come up in SACs and exams. All right, everyone, fantastic effort today. And that wraps up the chapter 1.9 Intermolecular Bonding. All right, before you leave, if you found this lesson helpful and want support with your VCE chemistry, you're always welcome to join our classes at Almighty Choice Tutorials. In our sessions, we don't just memorize the content, we focus on actually understanding why behind chemistry concepts. We break up difficult topics down step by step, simplify exam questions, and teach students exactly how to write high score VCE responses. Our classes include small group learning details, explanations, exam strategies, practice question, and revision support, and ongoing feedback. A lot of students struggle in chemistry because schools move too fast. Here we slow down things, explain concepts clearly, and build confidence properly. If you want to improve your understanding, boost your SAC marks, and feel more confident going into exams, feel free to contact Almighty Choice Tutorials. Thanks again for watching. Try helping and supporting each other.